So here we start looking at aromaticity. And in this section, we'll both get into what it means for a compound to be aromatic, as well as some nomenclature. And we're going to start here with the nomenclature for aromatic compounds. And some aromatic nomenclature is very, very simple and straightforward, but aromatic nomenclature is also made a lot more annoying by being the functional group that probably has the most um, commonly used common names, names that don't fit the IUPAC system. The other piece that can be annoying at times is that there's basically three different ways that we have to look at naming aromatics. We're going to start here with monosubstituted, which at first are going to seem very easy. Then disubstituted sort of follow their own pattern, and then if there's three or more substituents, we do them a different way. So why do I say monosubstituted should seem easy? Well, in many cases, such as this one, with only a single substituent, we just name the substituent and then the parent, which is of course benzene. So here we just have bromobenzene. And this is the case for any monosubstituted aromatic. Which would make this ethylbenzene. Again, just name the group followed by benzene. Probably seems pretty straightforward so far. The problem, as we said, is there's a lot of aromatics, especially monosubstituted, that are known by their common names. So for example, this one, which we might think just looks like methylbenzene, is known by the name toluene. And as we're going to see here, we have common names with an amine, alcohol, aldehyde, carboxylic acid, and even things like an alkene, as well as a methyl ether. So with the amine, we have aniline, the alcohol is phenol, the aldehyde is benzaldehyde, the carboxylic acid one we've seen many times before. We know this is benzoic acid. With the simple alkene coming off, we have styrene. And with the methoxy group, we have anisole. And pretty much every case with these common names, you've got to know the common names because those are what get used. All right, so that's monosubstituted. What happens for disubstituted? Well, in some ways, disubstituted isn't so bad because there's only three ways that you can have a disubstituted aromatic ring. And we'll draw them here. And these, if we were thinking about these like a normal ring, we might call these 1, 2, 1, 3, and 1, 4. And we still can call them that in the case of an aromatic ring. It's just those don't get used as often. And so the more common way to do this is that the 1, 2 is known as ortho, 1, 3 is meta, and 1, 4 is para. And we do abbreviate those typically as O M, and P. So if we had a compound such as this one, the only real difference between this and things that we've learned before is the use of ortho, meta, and para. So this is still going to be a benzene, and we have two substituents, bromine and the chlorine. And as always, we put them in alphabetical order. So this is bromochlorobenzene. Now we just need the ortho, meta, or para to indicate whether these two groups are 1,2, 1,3, or 1,4. Since the bromine and chlorine here are next to each other, that's going to make them ortho. And so we would call this O-bromochlorobenzene. Now you can write out the ortho. So if you call this ortho-bromochlorobenzene, would also be correct. You could also use the numbers and say 1-bromo, 3-chlorobenzene, and technically that's also correct. But ortho, meta, and para are the more common way and the more recognizable way to do these. So here's another example. So now we have a fluorine and a methyl group, and because they're 1,4, we would call this para-fluoromethylbenzene. Again, putting those in alphabetical order. However, we can actually abbreviate this further, because we learned a few minutes ago that methylbenzene has a common name of toluene. And so instead, we can combine those, and instead of benzene being the parent name, we can make toluene be the parent name. And in that case, this just becomes para-fluorotoluene. Again, technically either one is correct. The bottom one, the simpler one, is a better name for it, but in theory, either one is correct. And so again, here we can see we've got another compound that has, is going to have one of our common names, because we've got the carboxylic acid group. So now, again, instead of using benzene as our parent name, we can use benzoic acid. With benzoic acid here, we have an isopropyl group. And then to reflect that the relationship of the two groups is 1,3, we would call this meta, or M-isopropyl benzoic acid. Now, there are also some common names for certain di-substituted compounds that we should be aware of. And the two groups that we should be aware of are when we have either two methyls or two alcohols. And having two methyls is a little bit easier than the two alcohols, and that's because we use the same name, just ortho, meta, or para. But when we have two methyls, it's referred to as xylene. So we can have orthoxylene, metaxylene, or paraxylene. The more complicated one is having two alcohols. So if the two alcohols are ortho to each other, it's known as catechol. If they're meta, we have resorcinol, and if they're para, it's known as hydroquinone. All right, so that's our di-substituted aromatic nomenclature. What about more than two substituents? Well, more than two substituents is basically like a cycloalkane in terms of how we handle the naming and numbering. If you recall, with more than in a cycloalkane, we pick the position that would give us the lowest first number, followed by the lowest second number. And so if we do that for this compound here, we would get 4-hydroxy, 1,2-dimethyl benzene. And again, that's following all of the same rules that we learned, in Organic 1 for cycloalkanes. Now, that being said, in this example, you can see that again, we have a common name that's possible. With the OH group, we know that we would call that phenol. Well, how does that change our name? Well, first of all, we don't need to list the hydroxy anymore because we've combined that into benzene. But in addition, if we're using one of these common names as our parent, that redefines where carbon number 1 is. So as soon as we use phenol, that means the OH group is at carbon number 1. And so instead of numbering it the way we did above, we'd now have to number it starting with the OH group and go the direction that gets us to a substituent sooner. And so we would end up with 3,4-dimethyl phenol. So not a lot different, but again, the key here is that if you're going to use the common name, and generally we do when it's available, that defines which carbon is carbon number 1 automatically.